For our third derivatives example, we have, again, another position time function. So x of t is the position in meters of a particle t seconds after it begins moving. V is the velocity in meters per second. A is the acceleration in meters per second squared. And the difference is this time is they give us the acceleration function to start with, where the acceleration actually changes over time. It starts out and it's a constant 2 meters per second, and then after 2 seconds it's at 0, so the acceleration is flat, and then after that the acceleration is actually negative 2 meters per second for the final 2 seconds. And it wants us to sketch plots of each of acceleration, velocity, and position. So then, as always, we set up our paper. Our given are, again, time is in seconds, x of t is the position in meters, and so on. We've got our piecewise function broken up into parts and what we need there. So we start with part A, sketching acceleration. So sketching the acceleration, obviously the easiest part of it. We just have to take each part of the function and graph it. So we set our coordinate system. T is on the x, t is on the horizontal axis. We have to go past 6, starting at 0. Acceleration's on the y-axis. We know it's in meters per second squared. For the first 2 seconds, so from 0 to 2, it's at positive 2. Right after 2, so we have a hole at 2. But after that, from 2 to 4, it's at 0. And then a hole at 4, it goes to 6. So that part easy. We'll move on to the next part, which is sketching velocity. Sketching velocity, not as quite as straightforward, because if we think about it, we've done these past where we've gone backwards. Now, how do we figure out what the function of velocity is? Well, we know that the slope, the derivative or the slope of velocity comes from acceleration. So that means that these values would represent the slope, and since they're constant values, then v of t must be a constant value, or must be a linear function. So it's going to change. It's going to change depending on what we're doing. So from 0 to 2, v of t is going to be that slope times t plus some number. Where that's our acceleration. And this is actually going to be our initial velocity. So what is our initial velocity? Well, v of 0, we assume it starts out at 0. That before anything begins, we have to, it begins moving at time 0. So it initially starts out at 0. So that means if v of 0 is 0, that's the same as v0. So for this part, v of t is just 2t. Okay? But what about from 2 to 4? Well, from 2 to 4, the acceleration is 0. So v of t just has to be some constant value. And maybe to keep those clear, I'll call this that constant 1 with 0. Well, so v of t just has to be, v of t is just a constant value. So what is that constant? Well, if it's not changing once it gets there, it has to be whatever it was whenever we started doing this. So it has to be that c2 is equal to the velocity at 2, which is 2 times 2, and it's 4. So during this stretch, v of t equals 4. So what does it equal during the last stretch? Well, during the last stretch, 4 again, it's going to be, we think back, what is the acceleration? Well, the acceleration is negative, so that means our slope is going to be negative 2t plus the third constant. And what we know has to be true is that at 4, it has to match up. It has to be whatever velocity was happening at 4 still has to be that. So v of 4, well, what was the velocity then? It just equals 4. Has to be negative 2 times 4 plus c3. So this line is going to look something like that. And we can solve for c3 and get that c3 must be equal to 12. So during this stretch, v of t is equal to negative 2t plus 12. So now we have velocities. We have that velocity, and we have that velocity during that region. So if we get them all, let's see if I get them all on the screen. Yeah, so when we're trying to sketch velocity, we've got our 3 velocities, and then we will just have to make our sketch. Maybe we need to zoom out just a little bit to be able to see. So we'll start by setting up our graph, v of t. We know that we have to go out to 6 seconds. We know that the way it worked out, it started at 0, was increasing until it got to 4, leveled out for a while, and then went back down. We know during this first stretch it has a slope of 2, and it looks exactly like 2t, so as it goes over 2, it's going to go up 4. And then during the middle stretch, it's going to level out because acceleration is 0. So it stays constant until it gets to 4 seconds. And then at 4 seconds, it starts going down at negative 2. And because the values of those accelerations and the times they lasted were the same, we could get, if we plugged in 6 into that last equation, we would get it back down to 0 seconds, which is the way this one worked out. So there's our velocity function, and part C is going to ask us to sketch x of t. So again, if we want to try to sketch x of t, we have to break it down into the different parts. We look at what is going on during each part. So we start with the 0 to 2 stretch. So we know the velocity during that first part from 0 to 2 was 2t, and we know that has to do with what the derivative of thing is. So we have to think backwards from the things we've done before, and what would have a, we know this is the derivative of this. So if we think backwards, what has a derivative of 2t? Well, we've played with this many times, these functions, and we start to remember that I can get it by adding one, by raising this power and dividing by the new one. So t squared, if I went this way, would end up with the derivative of 2t. The other part I have to think about is there can still be a constant value on there. That we have that because if I had a constant value, I took the derivative, I would get there. So really what we're talking about doing here, and we didn't say it, and we really did this with the last part too, is we're taking an antiderivative, which is simply going the opposite direction with the derivative. Instead of starting with this and taking a derivative, we're going to do the antiderivative. So we need to know that. And again, we have to figure out what that constant value is, so we need some sort of condition to meet that. Well, again, we know that x of 0 has to equal 0. So 0 squared plus c has to equal 0, so c equals 0. So it turns out for the first part, x of t is just equal to t squared. Thinking about the second segment, from 0 or from 2 to 4, we know the velocity was just a constant function, 4. So if we wanted to take an antiderivative of 4, then we know that x of t is going to be 4t plus, we have another constant value. And the constant value that we know there, we know that x of 2 has to match up. We can't suddenly jump positions. So it's equal to 2 squared, which is 4. But that also has to equal four times 2 plus c 5. So that has to be a part of this same function. So we can set those two things equal to 0. So 4, I'm not to 0, but to each other. So equals 8 plus c5. So c5 must be negative 4. So for here, x of t must be equal to 4t minus 4. And we found what the equation is for the middle part. I'm going to go back and underline the first part up there. All right, so that gives us two of our segments. The final segment. Again, velocity for the last segment was equal to negative 2t plus 12 was our function there. We're going to do antiderivatives. So if it was negative 2t, we're going to actually end up with negative t squared plus, that will get a t on it, and we'll have another constant. And again, the thing that we have to know is that it has to match up with 4. So x of 4, which was 4 times 4 minus 4, which is 12, has to be what I get from it on this side, which is negative 4 squared plus 12 times 4 plus c6, which gives me 32 plus c6. So I would get that the constant to set those two things equals must be negative 20. And so x of t on this part must be negative t squared plus 12t minus 20. And so now I have three parts of a function, three parts of this function. Let's see if I can get them all on the screen. Well, I can't get the parts, but from 0 to 2, it's t squared. From 2 to 4, it's a straight line, 4t minus 4. And for the last part, it is another parabola, negative t squared plus 12t minus 20. So let's see what that sketch might look like. Okay, so we're trying to sketch this function. We set up our axes. T is in seconds, x is in meters. You can guess that I made the scale. Well, we know we're going from 0 to 6 seconds. I've made this scale fit what we're going to need, and we'll talk about that in a minute. So what do we know from working the previous part of the problem? Well, we know that for the first part, it looks like t squared, and we know that that starts at 0, 0. And so we know that it goes from 0 to 0. We know that at 2, it's at a value of 4. So we also know it's going to meet right there. So this part is just going to look, again, like the start of a parabola. It'll go to there and stop. from 0 to 2. From 2 to 4, it looks like the function 4t minus 4. And the important part of that is, without even being able to see where it crosses the axis, we know it has a slope of 4t. And so we also know that it ends, because we had to use it down here, at 12. So from 2 to 4, 4 being right there, we know it's a straight line going from 4 to 12. And then what happens on the end, we know that it is a parabola with a negative coefficient, so it's a parabola facing down. Good idea, which I just kind of added in there, is if we go ahead and quickly calculate what it is at the end point. So if we calculate x of 6, we plug that in there, we get 16. So we know at 6, it's going to be up here at 16. We already knew that at 4, it's at 12, because we had to have that count to make things work. And so that part is going to look something like that as a parabola. So if we zoom out and kind of think about all three of these graphs together, see if I can get them lined up, without necessarily even remembering what the function was. So there are our three graphs. We had acceleration was 3 flat lines, which gave us, for velocity, positive slope, 0 slope, negative slope, which gave us for the, if I get these right, they'll line up left to right pretty well too, which gave us for position, parabola facing up, straight line when we had 0 slope, and parabola facing down when we had a negative line for our velocity. So, yeah, that's how we can combine different parts and put them all together and make a graph out of it and connect things. So, really useful to kind of see how those things all interlink.